Welcome to solverfy.
We are given that the radon gas forms by alpha decay, so we know the final product is an alpha particle plus the radon gas. What we don't know is what is the initial reactant, and what is the initial parent nuclide. To find that, we need to look at the total protons and total nucleons, because we know that they must be conserved throughout the decay. So on the right hand side we have total proton number of 88, so likely that the parent nuclide must have 88 protons. The total nucleons is 226, right? So we must have 226. Looking up the periodic table, the element with 88 protons is radium, right? And so this must be our parent nuclide, and this will be the entire decay equation. Now for the next part, we need to find what is the kinetic energy of the alpha particle, but we are assuming, right, assumption is that the kinetic energy of our parent nuclide, the daughter nuclide, that is the radon, is equals to 0, right? So it doesn't move. So all the energy that was released in this decay reaction actually goes into our helium nuclide, right, or the alpha particle. And so we can equate the Q value of this decay equation to the kinetic energy of our alpha particle. The Q value of this equation can be obtained by taking the change in the masses of the nuclides multiplied by c squared. The change in the masses is taking the mass of radium, minus the mass of the alpha particle minus the mass of the radon gas. So all these values you have to look up through online resources. So for radium is 226.0254. For the alpha particle, and finally for the radon. C square, we're going to use the more convenient form, 931.5 MeV per U, since we are dealing with atomic mass units, right? So we can quickly get the energy in terms of MeV, which in our case is 4.87 MeV. So this is the Q value of, the kinetic energy of our alpha particle, assuming that all the kinetic energy, all the energy released goes into the kinetic energy of the alpha particle. From here, we will need to look at conservation of momentum in order to find what is the momentum of the daughter nuclide and the alpha particle. So we are assuming that the initial radium was stationary. That is, the total momentum of the system must be 0. So the final momentum of the system must be 0 as well. And this tells us that the magnitude of the momentum P of the alpha particle must be equal in terms of magnitude of the radon, right, or the daughter nuclide. So from the energy that was calculated from before, we are able to get the momentum of our alpha particle, right? We just equate this kinetic energy to P squared over 2m, so that our momentum of the alpha particle is equals to square root of 2m ke. Now we have all the values that we already need. Alright, we just have to substitute the various masses in. So for the mass of the alpha particle, we already have over here. Kinetic energy, we already have. And to make the atomic mass into a more convenient form, we're going to multiply that by 91.5 MeV per C square per U, right? So one atomic mass unit is equivalent to 91.5 MeV per C square. Right, this is the unit conversion. This will make the calculations simpler. So we got to convert this mass. We multiply this by the conversion factor over here to convert the mass into MeV per C square. Right, our Ke is in terms of MeV, right? So we'll get MeV squared per C squared. And so our final answer over here, we will get 190.6 MeV per C. So this is another units for momentum. Alright, and we know that because of the conservation of momentum, the momentum of our daughter nuclide must be the same as the momentum of the alpha particle, and so momentum of radon is also 190.6 MeV per C. Now the last part of this question, we want to find the kinetic energy of our daughter nuclide to confirm that, you know, indeed most of the kinetic energy goes to the helium nuclide, so we can make the original assumption. And we can find kinetic energy by taking p squared over 2m. But in this case, we want to find for the daughter nuclide, right? So that is for the radon. We already found that the momentum is 119.6 MeV per C. The mass for the radon is 222 U, and we got to convert the U, right? We do the same conversion again. We multiply this by 91.5 MeV per C square for 1 U, right? So convert atomic mass units to MeV per C square, so that we can actually cancel out the C square, right, at the top, and we get our answer in terms of MeV, which is 8.78 times 10 power minus 2 MeV, which is indeed much lower than our original alpha particle kinetic energy, right? Right, the kinetic energy of the alpha particle is 4.871 MeV, which is much larger, order of magnitude of 2 larger. And because the kinetic energy of radon is less than 2% of our kinetic energy of the alpha particle, we can say that our original assumption that most of the kinetic energy goes to the alpha particle is correct and valid.